There is a number in physics that you were never told about in school. 10 to the negative 31 seconds. It is the time it takes for a single grain of dust floating in air to lose its quantum nature entirely, to go from existing as a superposition of possibilities to being locked into a single definite state. For scale, light crosses a proton in about 3 times 10 to the negative 24 seconds. This process is 10 million times faster than that. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon, links in the description. It is faster than the end of cosmic inflation. It is faster than any known physical process except phenomena at the Planck scale itself. And that number means that the classical world, the world of solid objects and definite positions and things that exist in one place at a time, is not the default state of reality. It is the product of a violent, ceaseless, incomprehensibly fast process that the environment performs on every macroscopic object in the universe, every second, without pause. That process was discovered in 1970. It was buried for nearly 2 decades, and its deepest implication is still, right now, an open question that physics cannot answer. The process is called decoherence, and it is not subtle. A single grain of dust floating in the air in front of you right now is being hit by roughly 1 billion air molecules every second, and each one of those collisions is doing something specific. It is destroying quantum information. It is erasing superpositions. It is forcing that grain of dust to commit to a single position, a single state, a single version of itself. And it is doing this so fast that if you stretch 10 to the negative 31 seconds to last 1 full second, an actual second would last approximately 23 trillion times the current age of the universe. That is the ratio. That is how quickly the air around you is erasing the quantum nature of every macroscopic object you can see. I want you to sit with that for a moment. The reason you have never seen a chair in 2 places at once is not that chairs are too big to be quantum. The chair is quantum. Every atom in it is quantum. The reason you do not see its quantum nature is that the environment around it, the air, the light, the thermal radiation, is destroying that nature so fast that no measurement device humans will ever build could catch it happening. You are not living in a classical universe. You are living in a quantum universe that is being scrubbed clean of its own nature faster than any process except the Planck scale itself. And here is the part that should disturb you. The people who understood what decoherence meant spent the 15 years after Zeh's paper being told they were wrong, being told their careers were at risk, being told to let sleeping dogs lie. Not because the physics was wrong. The physics was correct. It was correct from the beginning, but because the implication of the physics was something the establishment was not ready to absorb. And the implication is this: decoherence explains perfectly why you never see superpositions. It explains why the classical world looks the way it does. It explains the disappearance of quantum weirdness at macroscopic scales so thoroughly and so quantitatively that there is essentially no remaining debate about the mechanism. But it does not explain why you see one outcome. It does not explain why, when that grain of dust is forced to pick a side, it picks the side it picks. After decoherence has done its work, the mathematics of quantum mechanics still says every possible outcome exists. The math does not choose. Nothing in the physics chooses. And the question of what does choose, or whether anything chooses at all, is the deepest unsolved problem in the foundations of physics. It has been open since 1970, and it is still open right now. That is what this video is about. Not decoherence as a trivia fact. Not decoherence as a textbook concept you memorize and move on from. Decoherence as a discovery that should have rewritten our understanding of reality and instead got locked in a drawer for 2 decades because the people who controlled the drawers did not want to deal with what was inside. And I want to be clear about why this matters to you, specifically. Right now, sitting wherever you are sitting, your body is a macroscopic object. Your brain is a macroscopic object. The air you are breathing, the light hitting your retinas, the sound waves entering your ears, all of these are decohering every quantum system they interact with at speeds that make the blink of an eye look geological. The classical world you experience, the world where things have definite positions, where events have definite outcomes, where you have a definite past and what feels like a definite future. That world is being constructed for you, around you, through you, by a process you were never told about. And the people who understand that process best, the people who have spent their careers studying it, cannot agree on what it means about the world you are living in. Some of them think it means the world you experience is the only one. Others think it means your world is one of an incomprehensibly vast number of equally real worlds, all coexisting, all invisible to each other, all generated by the same mechanism that makes yours feel solid. That disagreement is not a detail. It is the single most consequential open question in the history of natural philosophy. And it starts with a paper published in 1970 by a nuclear physicist in Heidelberg that almost nobody read. Heidelberg, West Germany, the late 1960s. Dieter Zeh was not a philosopher. He was not a quantum foundations enthusiast. He was a nuclear physicist. Born in 1932 in Braunschweig, he had studied under Johannes D. Jensen at the University of Heidelberg, the man who would share the 1963 Nobel Prize for developing the nuclear shell model. Zeh earned his PhD in 1962 doing theoretical nuclear physics. He spent time at Caltech and UC San Diego in the mid-1960s, working on the synthesis of heavy elements. He was, by every professional measure, a respectable mainstream physicist doing respectable mainstream work. The insight that would define his life and nearly destroy his career came not from philosophy or from reading obscure papers about quantum measurement. It came from nuclear physics, specifically from the time-dependent Hartree-Fock approximation, a standard mathematical tool used to model the behavior of nucleons inside heavy nuclei. Zeh was using this tool in the late 1960s, and something about it irritated him. The method treated the nucleus as though parts of it could be described independently, as though you could separate the quantum state of one group of nucleons from the rest. But quantum mechanics does not actually allow that. When particles interact, they become entangled. Their states become correlated in a way that means you cannot describe one without referencing the other. And Zeh realized that this entanglement, this refusal of quantum systems to stay independent, once they have interacted, was not just a technical nuisance in nuclear physics. It was the answer to the biggest open question in quantum mechanics. Here is what Zeh understood. When a quantum system interacts with its environment, with air molecules, with photons, with anything at all, it becomes entangled with that environment. The quantum information that used to be confined to the system leaks out into the environment. And once it has leaked out, Once the system's quantum state is correlated with billions of environmental degrees of freedom, the interference terms that are the signature of quantum behavior become effectively invisible. Not because they have been destroyed in any fundamental sense, but because they are now spread across so many environmental particles that no local measurement could ever detect them. The system looks classical. It appears to have definite properties, not because quantum mechanics has stopped applying, but because the quantum correlations have been diluted into the environment beyond any possibility of recovery. Let me make this more concrete, because I think the mechanism deserves to be understood, not just named. Imagine a single electron in a superposition of being at position A and position B. If the electron is perfectly isolated, that superposition is stable. The electron is, in a very precise mathematical sense, at both positions simultaneously. The interference between the two components of the superposition is what produces quantum effects, like the double-slit interference pattern. Now let a single photon scatter off the electron. The photon bounces off differently depending on whether the electron is at A or B. After the scattering, the photon carries information about the electron's position. The electron and the photon are now entangled. The total state is not electron at A plus electron at B. It is electron at A with photons scattered from A plus electron at B with photons scattered from B. The two terms are now correlated with different photon states. And if you measure only the electron, ignoring the photon, the interference between A and B is reduced. Not eliminated by one photon, but reduced. Now let a second photon scatter, and a third, and a billionth. Each one carries away a tiny bit more of the quantum information about the superposition. Each one correlates with the electron's position, entangling with it, spreading the information further into the environment. After enough scattering events, the interference terms are correlated with so many independent environmental degrees of freedom that recovering them would require simultaneously measuring every single photon that has ever interacted with the electron and performing a joint measurement on all of them coherently, which is, for any macroscopic object in any realistic environment, physically impossible. Not technologically impossible, physically impossible. The information is not gone. It is spread so thin that the universe itself does not contain enough computational resources to reassemble it. That is decoherence. It is not collapse. Nothing has been destroyed. The full quantum state of the universe, electron plus photons plus everything else, still contains all the information. The Schrödinger equation is still being obeyed, but locally, at the level of the electron, the quantum nature has become invisible. The electron looks classical. It looks like it is at one position, and the environment has accomplished this, not through any special mechanism, but simply by interacting with the system, in the way that every environment interacts with every system, all the time, everywhere. This was the core of decoherence, and Zeh arrived at it independently, without knowing about Hugh Everett III's 1957 relative state formulation, which had proposed a similar idea from a different angle. Zeh only learned about Everett's work through an article by Bryce DeWitt, and he revised his manuscript to reference it. But the key insight was his own, arrived at through the internal logic of nuclear physics, not through philosophy. He wrote it up. The paper was titled On the Interpretation of Measurement in Quantum Theory, and then he tried to get it published. What happened next should make you angry, because the paper was correct. It contained no mathematical errors. It made testable predictions, and it was rejected. One reviewer returned the manuscript with the verdict, and I want you to hear the exact words: "This paper is completely senseless." The stated reason for rejection was that quantum theory does not apply to macroscopic objects. Think about that. A physicist submitted a paper showing how quantum theory explains why macroscopic objects appear classical, and the reviewer rejected it on the grounds that quantum theory does not apply to macroscopic objects. The very phenomenon the paper was explaining was being used as the reason the paper was wrong. It was Eugene Wigner, the Hungarian-American physicist and Nobel laureate, who rescued the paper. Wigner helped Zeh find a publisher, and the paper appeared in the inaugural issue of Foundations of Physics, Volume 1, pages 69 through 76, in 1970. Wigner also arranged for Zeh to attend the 49th Enrico Fermi Summer School at Varenna on Lake Como in 1970, a conference organized by Bernard d'Espagna that historian Olival Freire later called the Woodstock of quantum dissidents. The attendee list reads like a who's who of people the physics establishment would rather not have in the same room: John Bell, Abner Shimony, Bryce DeWitt, David Bohm, Franco Selleri. Wigner himself included Zeh's decoherence proposal among 6 approaches to the measurement problem that he presented to the conference. But the establishment's reaction was not curiosity. It was hostility, and it was personal. An anonymous physicist sent a letter to Zeh's own doctoral supervisor, Jensen, the Nobel laureate, about a preprint of Zeh's work. The letter has been preserved in archives and was quoted by historian Christian Camilleri. It opened with a pun on Zeh's name, which in German sounds like the word for toe. I make it a rule of life, as far as avoidable, not to tread on any toe, the letter read. But the receipt of a preprint written by a certain Dr. Zeh from your institute compels me to deviate from this rule. I have every reason to assume that such a concentrate of the wildest nonsense was not distributed with your blessing. Jensen himself, Zeh's own mentor, responded by warning Zeh to let sleeping dogs lie. In German, schlafende Hunde soll man nicht wecken. And the consequences were not just social. Lee Smolin, reviewing Adam Becker's book What is Real for Physics Today, wrote that he was shocked to read that as late as the 1980s, Dieter Zeh's work on decoherence theory had serious consequences for him, and disastrous ones for his students. The American Physical Society maintained a formal policy under editor Samuel Goudsmit, urging referees to summarily reject papers on the foundations of quantum mechanics, particularly anything involving hidden variables or alternative interpretations. The message was clear: these questions are settled. Stop asking them. I want to stop here and make sure the weight of this lands. A physicist discovered the mechanism by which the classical world emerges from quantum mechanics. He published the result in 1970. It was correct, and instead of becoming one of the most celebrated insights in 20th century physics, it became a professional liability. His students suffered. His colleagues distanced themselves. The paper sat in a niche journal, cited by almost no one, for over a decade, not because it was wrong, because it was uncomfortable, because it implied something that the guardians of the Copenhagen interpretation did not want to confront. And that something is what we need to talk about next. But first, you need to understand what the numbers actually say, because the numbers are the part of this story that should have made front-page news and never did. And they come not from Zeh's original 1970 paper, but from a follow-up published 15 years later that took the abstract concept of decoherence and turned it into one of the most viscerally disturbing calculations in all of physics. In 1985, Joos and Dieter Zeh published a paper in Zeitschrift für Physik B, volume 59, page 223, titled The Emergence of Classical Properties Through Interaction with the Environment. What Joos and Zeh did was straightforward in principle and devastating in result. They calculated for the first time exactly how fast decoherence happens for realistic physical objects interacting with realistic environments. Not in the abstract, not approximately, specifically. They started with a dust grain, a speck of matter roughly 10 micrometers across, about 100,000th of a meter, just barely visible to the naked eye if you squint. Mass approximately 10 to the negative 14 grams, a grain of household dust. And they asked a question that sounds simple, but had never been answered quantitatively. If this grain of dust were somehow placed into a quantum superposition of two locations separated by its own diameter, how long would it take for the environment to destroy that superposition? How long before the entanglement with surrounding particles made the interference terms undetectable? The answer depends on the environment, and the answers Joos and Zeh calculated are the numbers that I think every person alive should know, and almost nobody does. In air, at standard temperature and pressure, the decoherence time for that dust grain is approximately 10 to the negative 31 seconds. In the best laboratory vacuum humanity can create, the decoherence time is approximately 10 to the negative 14 seconds. And in the most empty space imaginable, the void between galaxies, where the only thing touching that grain of dust would be the relic photons from the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, the decoherence time is approximately 1 second. I need to make these numbers real for you, because I think the first one especially gets lost in its own extremity. 10 to the negative 31 seconds. There is no intuitive way to comprehend this number. So here is the comparison I keep coming back to. Light is the fastest thing in the universe. It travels at roughly 300 million meters per second. A proton, the nucleus of a hydrogen atom, is about 10 to the negative 15 meters across. The time it takes light to cross a single proton is roughly 3 times 10 to the negative 24 seconds. That is already an absurdly small amount of time, a timescale so brief that no human technology can directly resolve it. And the decoherence time for a dust grain in air is about 10 million times shorter than that. Here is another way to think about it. If you took 10 to the negative 30, 1 second, and stretched it to last 1 full second, then an actual second would last approximately 23 trillion times the current age of the universe. That is the ratio. That is how quickly the air around you is erasing the quantum nature of every macroscopic object you can see. And that is just air. The second number is almost as striking. 10 to the negative 14 seconds is 10 femtoseconds. Ahmed Sawale won the 1990 Nobel Prize in Chemistry for using femtosecond laser pulses to photograph individual chemical bonds breaking in real time. The Nobel Committee described 1 femtosecond as being to a second what a second is to 32 million years. And in the best vacuum human technology can produce a grain of dust still loses its quantum coherence in roughly this amount of time. One chemical bond vibration. That is all the universe gives you. Even in near-perfect emptiness, a speck of dust cannot remain quantum for a single molecular heartbeat. And then there is the third number, 1 second, which you might think sounds generous until you realize what it means. Even in the most perfect void between galaxies, where there are no atoms, no molecules, no starlight, nothing except the 411 photons per cubic centimeter left over from the Big Bang, relics from 13.8 billion years ago, at a temperature of 2.725 Kelvin. Even those ancient photons are enough to decohere a dust grain in about 1 second. The cosmic microwave background, the faintest residual energy in the observable universe, is enough to enforce classical reality on a piece of dust. There is nowhere to hide. There is no environment empty enough for a macroscopic object to remain quantum. The universe does not allow it. It enforces classicality everywhere, at all times, with a thoroughness that borders on the absurd. And here is a number that puts the thoroughness in perspective. The ratio of the decoherence timescale to the energy dissipation timescale, meaning the time it takes the environment to actually push the object around physically versus the time it takes to destroy its quantum coherence, is approximately 10 to the negative 40. As Zurek himself pointed out, even if the relaxation rate were of the order of the age of the universe, roughly 10 to the 17th seconds, quantum coherence would be destroyed in approximately 10 to the negative 23 seconds. The environment leaks quantum information out of macroscopic objects roughly 10,000 trillion times faster than it transfers any energy to them. Decoherence is not a gentle process. It is not a gradual fading. It is an assault. Joos and Zeh also pointed out something that I think deserves more attention than it gets. Without decoherence, without the constant environmental monitoring that forces classical behavior, quantum mechanics predicts that macroscopic objects should exist in quantum superpositions of macroscopically different states, and not just in principle. Zurek later calculated a specific example. Saturn's moon Hyperion, a potato-shaped rock roughly 270 kilometers across that tumbles chaotically as it orbits, would, without environmental decoherence from scattered sunlight and cosmic microwave background photons, occupy a quantum superposition of orientations spread over roughly 57 degrees, a moon the size of a mountain range, smeared across nearly 60 degrees of rotation, because the chaotic dynamics amplify quantum uncertainties exponentially. The only reason Hyperion has a definite orientation at any given moment, the only reason you could point a telescope at it and find it at one angle rather than a quantum blur, is that photons are constantly measuring it. The environment is watching, and what the environment watches becomes real. That phrase is going to take on a meaning I have not fully unpacked yet. Remember it. I want to push on these numbers a bit more because I think they reveal something about the structure of reality that gets lost when you treat decoherence as just another physics concept. The numbers are not just large or small. They reveal a hierarchy, and the hierarchy tells a story. At the bottom is the Planck time, roughly 5 times 10 to the negative 44 seconds. This is the timescale at which our understanding of physics itself breaks down, where quantum mechanics and general relativity become irreconcilable. Then, far above that, 13 orders of magnitude above the Planck time, is the decoherence time for a dust grain in air. Then, 17 orders of magnitude above that is the decoherence time in the best vacuum. Then, another 14 orders of magnitude up is the decoherence time from just the cosmic microwave background. And then many more orders of magnitude up, you reach 1 second, the timescale of human experience. What this hierarchy means is that between you and the quantum nature of the objects around you, there are approximately 31 orders of magnitude of decoherence, 31 powers of 10, separating your experience from the underlying quantum reality. That is not a gap. That is a chasm so vast that it dwarfs the difference between a hydrogen atom and the observable universe. And the chasm is not empty. It is filled with a relentless, ceaseless, unforgiving process that has been running since the first photons scattered off the first baryons in the early universe. Here is another way to feel this. When you look at the screen you are watching this on, photons are bouncing off that screen and entering your eyes at the speed of light. Each of those photons carries information about the screen's classical state, its brightness, its color, its position. But each of those photons is also a decoherence event. Each one entangles with the screen and carries away quantum information, contributing to the destruction of any coherence between macroscopically different states. Roughly 10 to the 20 photons per second are scattering off a typical object in a well-lit room. That is 100 billion decoherence events per second, per object, from visible light alone. Add thermal infrared radiation and you get even more. Add air molecule collisions and you are in the billions of billions per second. The classical world is not sitting quietly waiting for you to observe it. The classical world is being manufactured, moment by moment, collision by collision, photon by photon, at a rate so staggering that the result looks effortless. And here is an experimental fact that makes the theoretical predictions visceral. Physicists have been trying for decades to push the boundary of how large an object can be placed into a genuine quantum superposition. The challenge is entirely about fighting decoherence. You have to isolate the object from its environment so completely that its decoherence time becomes long enough to detect quantum interference. In 1990, Marcus Arndt and colleagues at the University of Vienna showed quantum wave interference for C60, Buckminster fullerene, a molecule of 60 carbon atoms with a mass of 720 atomic mass units. This was a molecule large enough to image in an electron microscope, showing quantum interference in a modified double-slit experiment. By 2011, the same group pushed to molecules of 430 atoms. By 2013, to 810 atoms, more than 10,000 Daltons. And the current record, set in 2019 by Yakov Fein, Marcus Arndt and colleagues, published in Nature Physics, Volume 15, page 1242, is quantum interference with functionalized oligoporphyrins of up to approximately 2,000 atoms and 25,000 Daltons. One of these molecules had the chemical formula C707H260F908N16S53, ZN4, composed of more than 40,000 protons, neutrons, and electrons. The molecules remained in coherent superposition for over 7 milliseconds in a 2-meter-long interferometer. Despite having roughly 6,000 internal vibrational modes and internal temperatures of hundreds of Kelvin. These experiments work precisely because the molecules are isolated in high vacuum. The researchers had to control decoherence from residual gas and thermal radiation photon by photon. and their measurements of decoherence rates from these sources matched theoretical predictions quantitatively. Every time they allowed slightly more environmental interaction, the interference pattern degraded by exactly the amount the decoherence models predicted. But here is the gap that should unsettle you. The largest molecule ever placed in quantum superposition has approximately 10 to the 4th atoms. A grain of dust has approximately 10 to the 12 atoms. That is 8 orders of magnitude, 8 powers of 10 between the frontier of quantum experiments and the smallest object Joos and Zeh analyzed. The technology is closing in year by year, molecule by molecule, but it has not bridged the gap yet. And until someone places a genuine macroscopic object, something you can see with your naked eye, into a quantum superposition and watches what happens, there remains a sliver of room for the possibility that something else is going on. That decoherence is not the whole story. That somewhere between 10 to the 4th atoms and 10 to the 12 atoms, something new happens, something we have not predicted. Probably not. The theory is extraordinarily well tested, but probably not is not the same as certainly not. And I think the honest thing to do is tell you that. Now I want to come back to the people, because this story has 2 protagonists, and the second one changes everything about how decoherence entered the world. If Zeh is the prophet who was ignored, Wojciech Zurek is the translator who made the prophecy legible to the establishment, and his path to decoherence is one of the more unlikely stories in 20th century physics. Wojciech Hubert Zurek was born on December 19th, 1951, in Bielsko-Biała, a town in Silesian Poland, behind the Iron Curtain, during the height of Stalinist rule. His parents were Maximilian Stanislav Zurek and Anna Katarina Piaskowska Zurek. He attended the first secondary high school of Mikołaj Kopernik in his hometown, and the formative moment of his intellectual life happened before he finished high school. Growing up in resource-scarce 1960s Poland, the teenage Zurek convinced his father to buy him a Polish translation of Richard Feynman's lectures on physics. This was not a trivial purchase under communism. Books were expensive relative to wages, and foreign scientific texts were not widely available. In a 2009 profile for the Foundational Questions Institute, Zurek recalled the experience. The first few volumes had the air of amazement and surprise, and astonishment at how the universe works, he said, and at how much we can understand about how it works. He described this as the beginning of an obsession. Zurek earned his master's in physics in 1974 from AGH University of Science and Technology in Krakow. He left Poland in 1975, during a period when limited academic exchanges were possible despite the Iron Curtain, and arrived at the University of Texas at Austin. His formal doctoral advisor was William C. Sheave, a specialist in statistical mechanics. He earned his PhD in 1979, but the person who truly shaped his scientific life was not Sheave. It was the man down the hall. John Archibald Wheeler had moved from Princeton to the University of Texas at Austin in 1976, and he was running a quantum measurement course that read like a syllabus from the future. On the reading list was Zeh's 1970 paper. Also on the reading list were works by Bell, Bohm, Everett, and Wigner. Wheeler's students and postdocs during this period included an extraordinary concentration of people who would later become founders of quantum information science. William Wouters, who would co-discover the no-cloning theorem, Benjamin Schumacher, who would coin the word qubit, David Deutsch, who would invent the quantum computer as a theoretical concept, Chris Fuchs, who would develop cubism, and Wojciech Zurek. I am telling you about Wheeler, not because it is interesting background, but because Wheeler is the invisible thread connecting the two most important ideas in the foundations of quantum mechanics in the 20th century. At Princeton, Wheeler had been Hugh Everett III's PhD advisor for the 1957 Many Worlds thesis. At Austin, he became Zurek's postdoctoral mentor for the Decoherence program. The man who supervised the proposal that every quantum outcome generates a new branch of reality also supervised the man who would explain why those branches cannot see each other. That is not a coincidence. That is an intellectual lineage, and it matters for understanding what decoherence actually means. Zurek's memory of Wheeler captures something about how the best science gets done. The time when I realized I could really contribute, Zurek recalled, rather than just stand by and be amazed, was when I was with Johnny Wheeler. And on Wheeler's teaching style, Zurek said something I think every institution in the world should hear. Not being afraid of saying I do not know, and in fact using that admission of ignorance as a springboard to make progress, was something I had not realized, at least not with that clarity. There is a famous anecdote that captures Wheeler's character perfectly. Zurek wrote to Kip Thorne after Wheeler's death, recounting a moment from Wheeler's classroom. After a half hour of carefully calligraphed derivations that covered several blackboards, Wheeler discovered an error had crept into his calculations early on. Without hesitation, and in capital letters that were larger than anything else on the blackboards, he wrote, "Wrong," and crossed out all the boards. A sense of liberation swept the class. Zurek wrote, "It was possible to be a great scientist and admit that you are wrong," in capital letters. Wheeler and Zurek co-edited the landmark anthology Quantum Theory and Measurement, published by Princeton University Press in 1983. It collected 49 seminal papers on quantum measurement and became the standard reference in the field. And I need to tell you about Wheeler's own contribution to this story because it connects directly to the question decoherence leaves unanswered. In 1978 and again in 1984, Wheeler proposed a thought experiment called the delayed choice experiment. The setup is a variation on the double slit. A photon approaches a beam splitter, which gives it two possible paths. At the end of the paths, the experimenter can either recombine the paths to create interference, showing wave behavior, or leave them separate to detect which path the photon took, showing particle behavior. Standard quantum mechanics. What Wheeler proposed was making the choice of measurement, whether to recombine or to detect, after the photon has already passed the beam splitter, after it has already committed, in some sense, to one path or two. The result, confirmed experimentally by Alana Spate and colleagues in 1984 and achieved in near-ideal form by Vincent Jacques and colleagues in 2007, is that the photon's behavior depends on the choice the experimenter makes after the photon has already entered the apparatus. If you choose to look for interference, you find interference. The photon behaved as a wave, traveling both paths. If you choose to detect which path, you find a definite path. The photon behaved as a particle. And the choice was made after the photon was already inside the apparatus. Wheeler pushed this to a cosmic scale. Imagine light from a distant quasar, billions of light years away, bent by a gravitational lens so that it takes two paths around a massive galaxy. The photons have been traveling for billions of years. and the choice of whether to measure interference or which path is made by you in your laboratory right now. Wheeler's conclusion was stark. No elementary quantum phenomenon is a phenomenon until it is a recorded phenomenon, brought to a close by an irreversible act of amplification. At the Santa Fe Institute in 1989, Wheeler unveiled what he called the it from bit doctrine. Every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits. He described reality as arising from a participatory universe in which physics gives rise to observer participancy gives rise to information, and information gives rise to physics. This was not mysticism. This was a physicist who had worked with Bohr, who had helped build the atomic bomb, who had coined the terms black hole and wormhole and quantum foam, following the logic of his own experiments to its conclusion. And that vision of information as foundational to reality is precisely the vision that Zurek inherited and formalized. Einselection is about information. Quantum Darwinism is about information. The environment selects information, copies it, distributes it. The classical world, in Zurek's framework, is not made of matter. It is made of information about matter, information that the environment has chosen to preserve and proliferate. Wheeler's it from bit became Zurek's pointer states and extantons. The teacher's intuition became the student's mathematics. And there is a thread here that connects to something deeply personal that I want to pull before we move on. If the classical world is a product of environmental information processing, then what about you? You are a classical object. You are made of atoms interacting with the environment. Your brain is a physical system subject to decoherence. The neurons in your brain fire or do not fire, and each firing is a classical event produced by an underlying quantum process that has been decohered by the thermal environment of your body. The sodium and potassium ions flowing through the ion channels in your neurons right now are classical because decoherence has made them classical. The electrical signals propagating through your cortex are classical because the environment, your own body heat, the water molecules surrounding each neuron, the thermal vibrations of each protein has forced them to be, which means your thoughts are classical products of decoherence. Your decisions are classical products of decoherence. Your experience of making a choice, of being a conscious agent who deliberates and decides, is happening in a branch of the wave function that was selected by environmental decoherence operating at timescales vastly shorter than any neural process. By the time a neuron fires, decoherence has already happened. By the time you become conscious of a thought, the quantum possibilities have already been pruned into classical definiteness. You are experiencing the aftermath of a selection process that happened faster than you could ever perceive. And if the Everett interpretation is correct, then in another branch, the neurons fired differently. In another branch, you made the other choice. In another branch, you are not listening to this. And none of those branches are more real or less real than the one you are in. They are all products of the same universal wave function, all separated by decoherence, all convinced they are the only ones. I still do not know what to do with that. I do not think anyone does. And I think the honest response is to say so, rather than pretend that any interpretation of quantum mechanics makes this comfortable. None of them do. The ones that avoid many worlds do so by adding mechanisms that have never been observed. The one that embraces many worlds asks you to accept that your sense of being a single person with a single history is a product of informational isolation, not ontological uniqueness. Neither option is comforting. Both are consistent with the data. And decoherence, which was supposed to explain the classical world and make everything tidy, instead revealed that the untidiness goes all the way down. But before that book, before the decoherence program fully crystallized, Zurek was involved in one of the most remarkable episodes in the history of physics. It is 1981. An independent physicist named Nick Herbert submits a paper to Foundations of Physics titled Flash, a superluminal communicator based upon a new kind of quantum measurement. Flash stood for First Laser Amplified Superluminal Hookup, which tells you something about Herbert's flair for naming things. The paper proposed using quantum entanglement and a device that could copy quantum states to send information faster than the speed of light. The referee was Asher Perez, and Perez did something extraordinary. He knew the paper was wrong. He knew faster than light communication was impossible, but he deliberately recommended publication. Here is what Perez later wrote. I was the referee who approved the publication of Nick Herbert's Flash paper, knowing perfectly well that it was wrong. I wrote that it was obviously wrong, but I expected that it would elicit considerable interest and that finding the error would lead to significant progress in our understanding of physics. He was right. Physicists raced to find the flaw in Herbert's scheme, and in August 1982, two independent papers landed almost simultaneously. William Wouters and Wojciech Zurek submitted their refutation to Nature. Dennis Deeks independently submitted his to Physics Letters A. The result was the no-cloning theorem. It is impossible to create an identical copy of an arbitrary, unknown quantum state. This is not an engineering limitation. It is a fundamental consequence of the linearity of quantum mechanics. The paper, published as A Single Quantum Cannot Be Cloned in Nature, Volume 299, pages 802 through 803, became one of the most consequential short papers in physics history. And no, I am not making that up about its length. 2 pages that guarantee the security of quantum cryptography, make quantum teleportation require the destruction of the original, prevent faster-than-light communication by entanglement, and fundamentally connect to why the classical world exists at all. Every time you hear about quantum encrypted communications or quantum key distribution, the security of those systems rests on the theorem that a young Polish émigré at a nuclear weapons laboratory in the New Mexico desert proved in 2 pages in 1982. And here is a detail that I think reveals something about how discovery works. The no-cloning theorem had actually been proved 12 years earlier by a physicist named James L. Park in a paper published in Foundations of Physics in 1970, the same journal, the same year as Zeh's decoherence paper. Park's result went completely unrecognized. Nobody cited it. Nobody built on it. It sat in the literature for over a decade, invisible, until Wouters, Zurek, and Deeks independently rediscovered it. 2 foundational results in quantum information theory, published in the same journal in the same year, both ignored for over a decade. That is not a coincidence. That is a field that was not ready to hear what its own mathematics was telling it. I want to linger on what Zurek's life looked like at this point, because the biography matters for understanding the science. Here is a man who grew up in communist Poland, who convinced his father to buy Feynman's lectures, who left his country at 23, who earned a PhD in Texas, who sat in Wheeler's classroom and watched him write "wrong" in capital letters on the blackboard. And now, in the early 1980s, he is at Caltech on a Tolman Fellowship, and he has just co-discovered a fundamental theorem of physics by refuting a faster-than-light communication scheme. He is 29 years old. After the Tolman Fellowship, Zurek joined Los Alamos National Laboratory in 1984 as a J. Robert Oppenheimer Fellow. Think about that trajectory for a moment. A boy from Bielsko-Biala, behind the Iron Curtain, walks into the laboratory where the first atomic bombs were designed. The laboratory named for J. Robert Oppenheimer, the laboratory where the Manhattan Project began. He is given the fellowship named for Oppenheimer himself, and he is there to work on the most fundamental question in physics. Not nuclear weapons, not applied science, the nature of reality, what it means for a quantum system to become classical, why the world looks the way it does. Los Alamos is an interesting place for this kind of work. It is a national security laboratory. Its primary mission is nuclear weapons stewardship. The hallways are full of people doing classified work on subjects you are not allowed to know about. And in the middle of that, Zurek was building a theory about how the universe decides what gets to be real. There is an irony there that I do not think is accidental. The laboratory that helped build the most devastating weapon in human history, the weapon that demonstrated quantum mechanics' power in the most brutal possible way, also housed the person trying to explain why quantum mechanics produces a definite world at all. The bomb works because nuclear physics works. Nuclear physics works. And why quantum mechanics produces definite outcomes, why the uranium atom decays at this moment rather than that one, why the chain reaction proceeds this way rather than some other way, is the question Zurek was asking, at the laboratory where the answer to that question has life or death consequences. Because here is where it connects to decoherence. The no-cloning theorem says you cannot copy an arbitrary quantum state, but the environment during decoherence does not copy the full quantum state of the system. It copies only certain preferred states, the ones Zurek would call pointer states, the ones compatible with the system-environment interaction. The environment performs a kind of selective copying. It spreads information about some states while destroying information about others. And the states that survive this process, the ones whose information gets redundantly encoded throughout the environment, are precisely the classical states you observe. The environment does not clone, it selects. And what it selects becomes reality. Zurek formalized this idea under the name Einselection, short for environment-induced superselection. He published the key papers in Physical Review D in 1982. The concept is this: when a quantum system interacts with its environment, the environment does not interact equally with all possible quantum states of the system. Some states become highly entangled with the environment and lose their coherence almost instantly. Other states, the pointer states, are the ones that become minimally entangled. They are the states that survive. They are, in a very precise mathematical sense, the states the environment allows to exist. For a dust grain interacting with air molecules, the pointer states are states with well-defined positions and momenta, the classical states you know from Newtonian mechanics. For a quantum system in a thermal bath, the pointer states are coherent states localized in phase space. For an atom in a cavity, the pointer states might be energy eigenstates. The point is that the environment selects the basis. The environment decides what set of possible states the system is allowed to appear in. You do not choose what to measure. The environment has already chosen for you. It chose before you arrived. It chose before you were born. But Zurek was not done. He pushed the idea further into territory that I find genuinely unsettling in a way that most popular science never conveys. In 2009, he published a paper in Nature Physics, Volume 5, page 181, laying out a framework he called Quantum Darwinism. And the name is not a metaphor. It is a precise description of a selection process. Here is the idea. During decoherence, information about the pointer states of a system does not just leak into the environment, it gets redundantly copied throughout the environment. When photons bounce off an object, each photon carries away a partial copy of information about the object's classical state. When air molecules scatter off the object, each molecule carries away another copy. The environment becomes a vast repository of redundant copies of classical information. And because there are so many independent copies, multiple observers can independently access this information without disturbing the system. When you look at a chair and I look at a chair, and we both agree we see the same chair, we are both accessing different fragments of the environment, different photons that scattered off the chair, and finding the same information encoded in them. We agree not because there is a single objective classical reality that we are both perceiving directly. We agree because the environment has made billions of copies of the classical information and distributed them everywhere. Zurek's analogy is vivid. It is like a big advertising billboard, he said, which floats multiple copies of the information about our universe all over the place. The Darwinian analogy is precise. Selection, the environment selects pointer states. Heredity, the copies inherit the properties of the original states. Proliferation, the copies spread throughout environmental degrees of freedom. What does not happen is mutation. Unlike biological evolution, the selection is deterministic. The fittest states, meaning the ones most compatible with the system-environment interaction, always win, every time, without exception. And here is where it gets worse. Because in his most recent work, published between 2022 and 2025, Zurek introduced a concept he calls extantons. An extanton is a composite object consisting of a system of interest at its core, surrounded by a halo of environmental records, photons and air molecules, and thermal radiation that carry copies of the system's pointer state information. These extantons, Zurek argues, are the real objects of classical physics, not the bare quantum system, not the abstract wave function, the system plus its cloud of environmental witnesses. These are what he proposes as John Bell's beables, the things that objectively exist in quantum mechanics. Think about what that means. The chair you are sitting on as a classical object is not just the atoms arranged in the shape of a chair. It is those atoms plus the photons that have scattered off them, plus the air molecules that have bounced off them, plus the thermal radiation they have emitted, plus every other environmental degree of freedom that has interacted with them and carried away information about their state. The classical chair is a quantum system wearing a coat of environmental records, and it is the coat that makes it classical. Strip the coat away, isolate the atoms from every photon and every molecule and every graviton, and the chair becomes quantum again. The chairness of the chair is not in the chair. It is in the relationship between the chair and everything around it. I need to pause here because I think the sheer strangeness of this gets lost in the technical language. What Zurek is saying is that objectivity itself, the thing that makes multiple observers agree on what they see, is not a property of objects. It is a property of the information structure of the environment. The world looks classical and objective because the environment has copied classical information and made it available to everyone. If the environment stopped copying, if decoherence stopped, the world would not look classical anymore. Objectivity is not a given. It is a service the environment provides, and it can be revoked. Think about what this means for something as simple as looking at a cup on a table. You see the cup. I see the cup. We agree the cup is there. We agree on its color, its shape, its position. We call this objectivity. We call it the real world. But what is actually happening at the level of the physics is that trillions of photons are scattering off that cup every second, each carrying away a fragment of information about the cup's classical state. Those photons enter your eyes and mine. They also scatter off the walls, the ceiling, the floor. They are absorbed and re-emitted by every surface in the room. The information about the cup is everywhere. It is in every photon in the room. It is redundantly encoded in the electromagnetic field, in the thermal radiation, in the air molecules that have bounced off the cup's surface. We agree about the cup not because we are both accessing the same objective reality directly. We agree because we are both accessing different fragments of the same environmental record. And those fragments all contain the same information, because the environment has copied it everywhere. If you turned off the lights, removed the air, cooled the room to absolute zero, and eliminated every possible environmental interaction, the cup would, in principle, begin to decohere more slowly. If you could somehow eliminate every single environmental degree of freedom, which is physically impossible but logically conceivable, the cup would become quantum. It would exist in superpositions of different positions, different orientations, different configurations. The cupness of the cup, its definite shape and position and solidity, would dissolve into a quantum blur. Not because the cup is not real, but because the cupness was never in the cup. It was in the relationship between the cup and everything around it. Now, we need to talk about the burial, because the story of decoherence is not just a story about a scientific discovery. It is a story about what happens when a scientific discovery implies something the establishment is not prepared to accept. And the mechanism of that burial is worth understanding in forensic detail, because the same mechanism is operating in physics right now, on other topics, with other uncomfortable implications. Camilleri's historical thesis, documented in detail in the 22 Springer volume From Quantum to Classical, is this: interpretation influenced reception. Zeh's decoherence work was inseparable from his commitment to the Everett interpretation, the many worlds interpretation. And the Everett interpretation was in the 1970s considered scientifically disreputable. It was not merely unfashionable. It was treated as a sign of philosophical confusion, of a failure to understand what good physics was supposed to look like. Zeh's commitment to the Everett interpretation, Camilleri wrote, undoubtedly served as a major obstacle to the wider recognition of his early theoretical contributions. I want to be specific about how the suppression worked, because vague claims about the establishment are not useful. The suppression was not a conspiracy. Nobody held a meeting and decided to bury decoherence. What happened was more insidious and more normal. It was the everyday operation of professional norms, career incentives, peer review processes, and social enforcement of acceptable questions. And it operated through 4 specific mechanisms. First, the Copenhagen establishment actively policed dissent. Leon Rosenfeld, Niels Bohr's close associate, attacked critics of the Copenhagen interpretation with extraordinary venom. He called David Bohm's hidden variable theory a short-lived deviation and wrote letters to journal editors urging them to reject papers that challenged complementarity. The American Physical Society, as I mentioned, maintained editorial policies under editor Samuel Goudsmit, discouraging foundational papers. The message from the gatekeepers was explicit. The interpretation of quantum mechanics was settled by Bohr. Further discussion is philosophy, not physics. Move on. And this was not subtle. In 1962, when Bohm and his student Jeffrey Bubb submitted a paper on hidden variables to Physical Review, they received a rejection letter stating that the journal's policy was to discourage papers on the foundations of quantum mechanics. Imagine submitting a paper on general relativity and being told the journal discourages papers on gravity. That was the environment. Second, the broader physics community treated interpretive work as beneath serious scientists. This was not just an attitude, it had material consequences. Funding agencies did not fund foundational research. Tenure committees looked askance at it. Graduate students were explicitly warned away from it. John Clauser, who won the 2022 Nobel Prize for his experimental tests of Bell's theorem, has described how his advisor at Columbia told him the work was a waste of time and that it would damage his career. Alain Aspect was warned by John Bell himself to make sure he had tenure before publishing his Bell test results. The career risk was real and widely known. Third, Zeh lacked institutional support in a way that was directly consequential. Unlike Zurek, who had Wheeler's protection and access to mainstream journals, Zeh was isolated at Heidelberg. His own supervisor had told him to stop. His colleagues avoided him. He published some of his most important work in the epistemological letters of the Ferdinand Gonzeth Association in Switzerland, a venue so obscure that the vast majority of working physicists had never heard of it. The ideas were correct, the distribution was invisible. And in science, distribution is everything. A correct idea that nobody reads might as well not exist. Fourth, and this is the one I find most troubling, decoherence was not rejected because someone found a flaw in the mathematics. Nobody showed that Zeh's calculations were wrong. Nobody demonstrated that environmental entanglement does not destroy coherence. Nobody challenged the physics. The rejection was sociological. It was based on what the physics implied, not on whether the physics was correct. And what the physics implied, at least as Zeh understood it, was the Everett interpretation. Multiple branches of reality, none of which is more real than the others, separated by decoherence into mutually invisible sectors. The guardians of Copenhagen did not want to hear this, so they did not listen. Zeh knew exactly what was happening. He wrote, "Years later, I am indeed surprised about the indifference of most physicists regarding the potential consequences of decoherence. And more pointedly, the dishonesty of the Copenhagen interpretation consists in switching concepts on demand and regarding the genuine or apparent collapse as a normal increase of information, as though the wave function represented no more than an ensemble of possible states." He called the 1970s the Dark Ages, of Decoherence. He maintained the personal website at decoherence.de, constantly updating it with new essays and revisions, a labor of love maintained by a man who knew he was right and knew the world was not listening. And the cost was not just to him. His students paid a price. When Lee Smolin wrote that Zeh's work had serious consequences for him and disastrous ones for his students, that was not rhetorical. Students who worked on decoherence and quantum foundations at Heidelberg in the 1970s and 80s faced a job market that treated their research area as professionally illegitimate. They had difficulty finding academic positions. Their letters of recommendation from Zeh were, in some departments, liabilities rather than assets. The intellectual lineage that should have been a source of pride, working with the man who discovered one of the most important mechanisms in physics, was instead a mark against them. Imagine finishing your PhD, having done real, correct, important physics, and finding that the very fact that you did it makes you unhireable. That is what the suppression of decoherence cost in human terms. Not just one man's career. A generation of students who were punished for working on the right problem at the wrong time. Klaus Kiefer, who later became a professor at the University of Cologne and edited the memorial volume for Zeh, is one of the students who survived. Others were not so fortunate. The historical record does not preserve the names of the ones who left physics entirely, who gave up on careers in a field that told them their research was worthless. That is how suppression works in science. It does not just delay ideas, it wastes lives. 3 weeks before his death, Zeh was still commenting on Peter Woit's physics blog, Not Even Wrong, noting that decoherence had now been experimentally confirmed. He died on April 15, 2018, while on holiday in the Black Forest in Germany. He was 85. Klaus Kiefer, his former PhD student, published an obituary in the International Journal of Quantum Foundations. Peter Woit wrote on his blog that Zeh was deserving of the Nobel Prize. He never received one. So how did decoherence go from the wildest nonsense to a foundational concept in physics? The turning point was Zurek, and the crucial difference was strategy. When Zurek published his key papers in Physical Review D in 1981 and 1982, he made a deliberate choice that Zeh never made. He kept the paper's interpretation agnostic, where Zeh had explicitly connected decoherence to the Everett interpretation and advocated for many worlds. Zurek focused on specific technical problems. The preferred basis problem, the dynamics of the density matrix, the emergence of effective superselection rules. He did not wave the Everettian flag. He did not challenge Copenhagen head-on. He presented decoherence as a tool, as a technical result, as something any interpretation could use. And that made it palatable to physicists who would have reflexively rejected anything stamped with the Everett brand. There is an irony here that I think Zeh himself would have appreciated. Decoherence, which Zeh always saw as the strongest possible evidence for many worlds, was accepted by the mainstream only when it was divorced from many worlds. The physics did not change. The framing changed. And framing, in science as in politics, determines reception. I want to dwell on this because I think it contains a lesson that extends far beyond physics. Zeh and Zurek discovered essentially the same thing. Environmental entanglement destroys local coherence and produces the appearance of classicality. Their mathematics were compatible. Their predictions were the same. But Zeh said out loud what the math implied, that all branches are real, that the wave function never collapses, that you are one component of a universal superposition. And Zurek said, Let us focus on the technical results and let each physicist draw their own interpretive conclusions. Zeh was punished. Zurek was rewarded, not because their physics differed, because their rhetoric differed. And I am not telling you this to criticize Zurek. His strategy was effective and it worked. Decoherence entered the mainstream because Zurek made it possible for Copenhagen loyalists to use the formalism without feeling that they were endorsing many worlds. That was pragmatic and probably necessary, but the cost was real. The cost was that the interpretive implications of decoherence, the deepest and most important implications, were systematically downplayed for decades. The formalism was accepted, the meaning was deferred, and we are still living with that deferral. The Joos and Zeh 1985 paper accelerated acceptance by providing the hard numbers without the interpretive commitment. Aaron Caldera and Anthony Leggett's 1983 papers on quantum Brownian motion provided complementary theoretical tools. Murray Gell-Mann and James Hartle's 1990 decoherent histories approach brought decoherence firmly into mainstream theoretical physics. And Zurek's 1991 article in Physics Today, titled Decoherence and the Transition from Quantum to Classical, brought the concept to a broad audience of working physicists for the first time. By the mid-1990s, decoherence was appearing in textbooks. By November 2018, the month Zeh died, 1,477 articles with the word decoherence in the title could be found on Arxiv's quantum physics section alone. From 0 citations and 1 hostile reviewer in 1970 to nearly 1,500 papers in 48 years. That is the trajectory of an idea that was correct from the beginning and whose only crime was being premature. But I want to flag something here because I think it matters for understanding how knowledge systems work. The mid-19s, that is 25 years after Zeh's original paper, 25 years during which the physics community could have been building on this insight, could have been developing quantum information theory with decoherence as a central tool, could have been designing quantum error correction protocols informed by quantitative decoherence models. 25 years. Lost. Not because the idea needed 25 years to develop. The Joos and Zeh numbers were available by 1985. The idea was fully formed by 1970. The delay was entirely sociological, and I want to make the cost of that delay concrete. Peter Shaw published his quantum factoring algorithm in 1994, the algorithm that showed quantum computers could break most existing encryption. That algorithm works by exploiting quantum superposition and interference. And it fails because of decoherence. Every quantum error correction code developed since Shaw's algorithm is a direct response to the phenomenon Zeh described in 1970. If the physics community had taken decoherence seriously from the beginning, if Zeh had not been told his paper was senseless, if the field had begun developing quantitative models of environmental decoherence 25 years earlier, where would quantum computing be today? I do not know the answer. Nobody does. But the question itself is an indictment. 25 years of potential progress on one of the most important technologies in human history, delayed because a reviewer thought a correct paper was nonsense, and a Nobel laureate told its author to let sleeping dogs lie. As Philip Bohr wrote in Quantum magazine in February 2026, this might have happened much sooner if researchers had not been discouraged for decades from asking questions about these foundational but unresolved issues. You'd think someone would have said something. Nobody did. Not publicly, not in a way that mattered, not until it was safe. Now I need to address something that the vast majority of popular science gets catastrophically wrong about decoherence. Because there is a misconception that has infected physics communication at every level, from YouTube videos to undergraduate textbooks. And it is this: the claim that decoherence solves the measurement problem. It does not. I want to be precise about what decoherence does and does not explain, because getting this wrong is not a small error. Getting this wrong means misunderstanding the most important open question in the foundations of physics. The measurement problem, as identified by Maximilian Schlosshauer in his 2004 Reviews of Modern Physics paper, has three sub-problems. 1. The preferred basis problem. Why are measurements made in particular bases rather than others? 2. The problem of non-observability of interference. Why do we not see macroscopic superpositions? 3. The problem of definite outcomes. Why does one specific result occur in any given measurement? Decoherence solves problems 1 and 2. Convincingly, Einselection dynamically selects the preferred basis. Environmental entanglement destroys interference terms so fast that no measurement could ever detect them. Those are real achievements, and they represent genuine progress. But decoherence does not solve problem 3, not even a little, not even in principle. And the reason is subtle, but critical. After decoherence has done its work, the reduced density matrix of the system, the mathematical object that describes the system's state after you trace out the environment, looks diagonal in the pointer basis. It looks like what you would get if the system were in one definite state and you just did not know which one. It looks, mathematically, like a classical probability distribution, a coin under a cup, either heads or tails. You just have not looked yet. But it is not a coin under a cup, and the distinction matters enormously. A proper mixture is what you get from classical ignorance. The system is in one definite state. You do not know which. Your uncertainty is about your knowledge, not about reality. An improper mixture is what you get from tracing out part of an entangled system. The reduced density matrix looks the same as a proper mixture, mathematically identical. No experiment measuring only the system can distinguish the two. But the system is not in one definite state. It is still part of a larger entangled superposition that includes the environment. The diagonal density matrix is not a classical probability distribution over definite outcomes. It is the local appearance of a global quantum superposition. I want to make this concrete because I think the abstraction hides the punch. Imagine you have a coin and you flip it and put a cup over it. The coin is either heads or tails. You do not know which. That is a proper mixture. Your uncertainty is about your knowledge. Reality is definite. Now imagine instead that the coin is in a quantum superposition of heads and tails, and it has become entangled with the air molecules in the room. If you look at just the coin, ignoring the air molecules, the math looks identical to the classical coin under a cup. Diagonal density matrix, 50-50 probability, looks like classical ignorance, but it is not classical ignorance. The coin has not landed on either side. The coin and the air molecules are in a joint superposition. Heads coin plus heads record air molecules in one branch. Tails coin plus tails record air molecules in the other branch. The branches do not interfere. They look separate, but neither branch has been selected as real. They are both there in the mathematics with equal status. This is the gap. This is the thing that decoherence does not bridge. After decoherence, the mathematics says the system plus the environment is in a superposition of correlated branches. One branch has the dust grain here and the environment recording here. Another branch has the dust grain there and the environment recording there. The branches do not interfere. They cannot see each other. Decoherence has made them effectively orthogonal. But nothing in the physics selects one branch as the real one and discards the others. Nothing. The Stanford Encyclopedia of Philosophy, revised January 2025, states this as plainly as I have ever seen it stated. While decoherence does explain why we do not observe superpositions of measurement results, it does not explain why we do observe measurement results in the first place. And the founders of decoherence theory knew this. Zeh himself wrote in his 2005 Seminaire Poincaré lecture, "Let me first emphasize that by decoherence, I do neither just mean the disappearance of spatial interference fringes, nor do I claim that decoherence without additional assumptions is able to solve the infamous measurement problem." Steven Weinberg, one of the most decorated theoretical physicists of the 20th century, noted in his lectures on quantum mechanics that there seems to be a widespread impression that decoherence solves all obstacles, and characterized Zurek's attempt to derive the Born rule from decoherence as clearly circular. Stephen Adler of the Institute for Advanced Study published a paper specifically titled "Why Decoherence Has Not Solved the Measurement Problem" in 2003, responding to Nobel laureate P.W. Anderson's claim that it had. And a 2016 survey of physicists found that 29% of respondents erroneously believed the measurement problem had been solved by decoherence. Nearly a third of working physicists think the problem is solved. It is not. I want to sit with that statistic for a moment. Think about what it means for how physics is taught and communicated. Imagine a survey of cardiologists finding that nearly a third believed heart disease had been cured. That would be a scandal. It would trigger investigations into medical education, but nearly a third of physicists misunderstanding the most important open problem in the foundations of their own field. And nobody treats that as a crisis. Nobody demands an accounting of how the textbooks got this wrong, how the popularizers got this wrong, how the classroom explanations got this wrong. The information just quietly fails to be communicated, generation after generation. And the misconception propagates. And it matters. It matters because every time a textbook says decoherence explains the quantum to classical transition and leaves it there, without the crucial caveat, a student walks away believing the measurement problem is solved. They believe the hard question has been answered, and then they never ask the hard question. They become a physicist who never asks why one outcome occurs, because they were taught that decoherence handles it. The suppression of Zeh's paper in the 1970s is dramatic and personal and makes for a good story. The quiet ongoing suppression of the real implications of decoherence through omission rather than hostility, through lazy textbook writing rather than active censorship, is less dramatic, but arguably more consequential. It is happening right now. It is happening in physics classrooms around the world. There is a second misconception I want to correct while we are here. You may have heard of Schrödinger's cat. You probably heard it presented as a fun illustration of quantum weirdness. Look how crazy quantum mechanics is. A cat that is both alive and dead. What you almost certainly were not told is that Erwin Schrödinger designed the thought experiment in 1935 not as a celebration of quantum mechanics, but as an attack on it. He was not saying, "Look at this wonderful quantum effect." He was saying, "Look at how absurd this interpretation is." He was performing a reductio ad absurdum, showing that the Copenhagen interpretation, taken seriously, produces conclusions so ridiculous that it must be incomplete. The cat was not meant to make you marvel. It was meant to make you worried. And decoherence, which shows exactly how and why the cat's quantum coherence would be destroyed in a fraction of a second by interactions with its own body heat and the air in the box and the photons in the Geiger counter, actually vindicates Schrödinger's worry. The cat would never be in a superposition in practice. Decoherence prevents it. But the question of why the cat ends up alive or dead, why one outcome rather than the other, is exactly the question Schrödinger was pointing at. And it remains unanswered. Now, the experiments. For decades, decoherence was a theoretical prediction. The numbers were calculated, the models were built, but nobody had directly observed the process in a controlled laboratory setting where you could watch quantum coherence being destroyed by environmental interaction in real time. That changed in 1996 when Serge Haroche's group at the École Normale Supérieure in Paris performed the first quantitative measurement of decoherence using rubidium atoms interacting with microwave photons in a high-quality cavity. The experiment was elegant and precise. They created a microwave field inside a superconducting cavity, a pair of mirrors facing each other with such precision that photons could bounce back and forth for 1/10 of a second before being absorbed, making roughly 1 billion round trips. They sent individual rubidium atoms through this cavity, one at a time, each atom carefully prepared in a specific quantum state. Each atom interacted with the microwave field briefly, entangling with it, and then continued on its way to a detector. What Haroche's team could do was prepare the microwave field in a superposition of two different coherent states, what physicists call a Schrödinger cat state, a quantum superposition of macroscopically distinguishable conditions. And then they could probe the field with successive rubidium atoms, measuring how quickly the superposition decayed. They watched, atom by atom, as the quantum coherence between the two states was destroyed by the environment, the tiny imperfections in the cavity mirrors, the residual thermal photons, the coupling to the outside world. The decoherence times they measured matched theoretical predictions. The curves matched. The models worked. David Wineland's group at NIST in Boulder produced complementary results using trapped ions, individual atoms held in electromagnetic traps and manipulated with laser pulses. They could prepare superpositions of the ion being in two different locations, separated by distances much larger than the ion's wave packet, and then watch the superposition decay. Again, the decoherence times matched the models. Haroche and Wineland shared the 2012 Nobel Prize in Physics for, as the citation stated, groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. It is worth noting what the Nobel Committee did not say. They did not say the prize was for solving the measurement problem. They said it was for methods, for tools. The tools work. What the tools reveal about the nature of reality remains contested. And I want to flag something about the timeline, because it matters. Haroche's decoherence experiments were in 1996. The Joos and Zeh paper calculating the decoherence timescales was in 1985. Zeh's original paper was in 1970. It took 26 years from the original theoretical insight to the first quantitative experimental confirmation. That is not because the experiments were impossible in 1970. It is because nobody was trying. Nobody was trying because the physics community had been told that these questions were not worth asking. The experiments came only after the theory had been rehabilitated, and the theory was rehabilitated only after Zurek repackaged it without the Everettian implications. The timeline is an indictment. And there is a dimension to this story that connects directly to your life in a way that the foundational physics might obscure. Decoherence is not just an abstract concept about the nature of reality. It is the central practical problem of quantum computing. Every quantum computer that has ever been built or is currently being built is, at its core, a machine designed to fight decoherence. The qubits in a quantum computer must be maintained in quantum superposition for long enough to perform computations. But the environment is constantly trying to decohere them, to entangle them with surrounding atoms and photons and thermal vibrations, to turn their delicate quantum states into classical noise. Every quantum error correction code, every cryostat cooled to millikelvins, every electromagnetic shield, every vibration isolation platform is a weapon in the war against decoherence. And that war is being fought with the theoretical tools that Zeh and Zurek developed. The irony is precise and bitter. Zeh's discovery, buried for 2 decades because it was deemed irrelevant philosophy, is now the single most important concept in a technology industry that may be worth trillions of dollars within your lifetime. The man who was told to let sleeping dogs lie helped create the theoretical framework that underpins quantum computing, quantum cryptography, and quantum communication. If the dogs had been let alone, if the questions had never been asked, the entire field of quantum information science would look fundamentally different, and it would be fundamentally poorer. Those experiments confirmed that decoherence was real and quantitatively predictable, but they did not test the specific predictions of quantum Darwinism, Zurek's framework for how classical information gets redundantly encoded in the environment. For that, you needed a different kind of experiment. You needed to be able to prepare a quantum system, let it interact with a small controlled environment, and then independently measure different fragments of that environment to check whether they all contain the same classical information about the system. You needed to verify the redundancy, the copying, the Darwinian proliferation of pointer state information. In 2019, a team spanning Ulm University, the Hebrew University of Jerusalem, NIST, and Los Alamos published the first experimental verification. The paper was Undon, Luzon, Swolak, Zurek, and Gillespie, revealing the emergence of classicality using nitrogen-vacancy centers. Physical Review Letters, Volume 123, Paper 140402. The system they used was beautiful in its elegance, a nitrogen-vacancy center in diamond. This is a defect in the diamond crystal lattice where 2 adjacent carbon atoms have been replaced by a nitrogen atom and an empty lattice site. The result is a single isolated electron spin that can be placed in quantum superposition and read out optically. You shoot a green laser at the diamond. The electron spin fluoresces red, and the brightness of the fluorescence depends on the spin state. It is essentially a single quantum bit embedded in a solid crystal, sitting on a lab bench at room temperature without cryogenics or vacuum chambers. Just a diamond with a defect. The environment was approximately 4 carbon-13 nuclear spins located about 1 nanometer from the nitrogen-vacancy center. Carbon-13 is a stable isotope of carbon with a natural abundance of roughly 1.1% in diamond. And these nuclei interact with the electron spin through the hyperfine interaction. This is the same physical process that limits quantum computing in solid-state spin systems. It is the same interaction that makes MRI machines work. And here it was being used not as a nuisance to be suppressed, but as the thing being studied. The environment was not the enemy. It was the subject of the experiment. What the researchers did was prepare the nitrogen-vacancy electron spin in a superposition, let it interact with the surrounding carbon-13 nuclei through natural hyperfine coupling, and then selectively measure individual nuclear spins using adaptive dynamical decoupling pulse sequences. This is technically demanding work. You are trying to read out the quantum state of individual atoms inside a crystal. Atoms that are sitting less than a nanometer from the electron spin while keeping everything else quiet. The fact that it works at all is a testament to decades of progress in diamond quantum sensing. They found exactly what quantum Darwinism predicts. Measuring just 1 carbon-13 nucleus was sufficient to learn most of the information about the electron spin's state. Measuring a second nucleus added a little more. A third added less still. And beyond that, you were getting diminishing returns. The mutual information between the system and each environmental fragment showed the characteristic classical plateau, the signature prediction of quantum Darwinism. The information was out there, in the environment, redundantly encoded, available to anyone who could read a single nuclear spin. That is objectivity. That is what makes your world look classical. Not because the information is in one place, because it is in every place, because the environment has copied it and scattered it everywhere. The paper concluded that this was the first laboratory verification of the process responsible for the emergence of the objective classical world from the underlying quantum substrate in a natural environment. Published, peer-reviewed, experimentally confirmed in 2019, and then in 2025, the most comprehensive confirmation yet. Zetian Zhu, Chiara Salise, Akram Tuil, and colleagues at Jazan University, the University of Houston, and Los Alamos National Laboratory published Observation of Quantum Darwinism and the Origin of Classicality with Superconducting Circuits in Science Advances, Volume 11, Paper Edix 6857 on August 1st, 2025. This time, the platform was superconducting transmon qubits. These are the same kind of devices that companies like Google and IBM use in their quantum computers. High-quality ones. Energy relaxation times of approximately 130 microseconds. Single qubit gate fidelity of approximately 99.97%. These are serious quantum computing grade devices, not toy demonstrations. The team built 2 configurations, a 12-qubit system with 2 central qubits as the system coupled to 10 environment qubits, and a 9-qubit system with inter-environment interactions that enabled information scrambling. I want to explain why the second configuration matters, because it addresses a criticism that had lingered over quantum Darwinism for years. In a real environment, information does not just flow from the system to the environment and sit there pristinely. The environment is itself a complex dynamical system. Environmental degrees of freedom interact with each other. Information gets scrambled, reshuffled, mixed around. Critics had argued that quantum Darwinism might only work in idealized environments where information stays neatly organized. The 9-qubit configuration was designed to test exactly this. They deliberately introduced inter-environment interactions that scrambled the information, and the signatures of quantum Darwinism survived. The redundancy persisted. The classical plateau in mutual information remained. Even when the environment was actively churning its internal state, the classical information about the system remained accessible and redundant. The environment does not need to be tidy. It just needs to interact. The results went further than anything previous. They observed the full information theoretic signatures of quantum Darwinism: mutual information saturation, vanishing quantum discord, whole-of-O information matching the predictions. They directly visualized the branching structure of quantum states in Hilbert space, the actual mathematical structure that underpins the emergence of classicality, and they showed that quantum Darwinism's signatures persist even when information scrambles within the environment, meaning even when the copies get shuffled and rearranged, the redundancy survives. The environment selects. The environment copies. The environment distributes. Every prediction confirmed. And still, the central question remains unanswered. Because here is what these experiments also show, and this is the part that I think deserves more attention than it has ever received in any popular treatment of this subject. The experiments confirm the mechanism of decoherence. They confirm the information flow. They confirm the redundancy. They confirm the signatures of quantum Darwinism down to the finest quantitative detail. What they do not show, what they cannot show, what no experiment has ever shown, is why one particular outcome was recorded rather than another. The 2025 superconducting circuit experiment is especially revealing on this point. The team could prepare a superposition, let the environment interact with it, and then measure the environment and find classical information perfectly distributed according to quantum Darwinism's predictions. But each time they ran the experiment, each time they prepared the same superposition and let it decohere, they got a random outcome. Sometimes the system ended up in one pointer state, sometimes the other. The probability distribution matched the Born rule perfectly. The mechanism of how information flows into the environment was exactly as predicted. But the selection of which outcome occurred in each individual run was random. Completely, fundamentally, irreducibly random. The theory predicts the statistics. It does not predict the individual event. And that random selection, that irreducible unpredictability of the individual outcome, is the measurement problem. It is the gap between the disappearance of interference and the appearance of a fact. Decoherence fills everything around the gap. It explains why the statistics work. It explains why you do not see superpositions. It explains why observers agree. It explains the preferred basis and the pointer states and the redundant encoding. It explains everything, except the one thing that makes your experience of reality feel definite and singular and non-negotiable. Why this outcome? Why now? Why here? I want to bring the human story to its conclusion before we go where this is all pointing. Dieter Zeh died on April 15th, 2018. He was on holiday in the Black Forest. He was 85. He had spent 48 years defending an idea that went from the wildest nonsense to a foundational concept in physics, from career poison to the theoretical backbone of a quantum computing industry worth billions. He never received a Nobel Prize. He never received the kind of mainstream recognition that Zurek eventually earned. He never saw the 2019 experiment that first confirmed quantum Darwinism in a laboratory, though the theoretical framework was already complete before his death. He never saw the 2025 superconducting circuit experiment that provided the most comprehensive confirmation yet. He never saw the Quantum magazine article in February 2006 that brought his story to a broad audience for perhaps the first time. 3 weeks before he died, he was still posting on physics blogs, still arguing for the Everett interpretation, still insisting that decoherence, properly understood, implies that all branches of the wave function are real. He never stopped. From 1970 to 2018, for 48 years, through professional isolation and personal cost, and the slow grinding vindication of watching the world come around to his physics while continuing to reject his interpretation, he never stopped. I remember authors claiming that decoherence saves us from the conclusion of many worlds. He wrote, near the end of his life, although precisely the opposite is true. That is a man who spent half a century being told he was wrong and never once flinched. Zurek's trajectory was different, but converging. After the Tolman Fellowship at Caltech from 1981 to 1984, he joined Los Alamos National Laboratory in 1984 as a J. Robert Oppenheimer Fellow. He rose to lead the theoretical astrophysics group in 1991 and was named Laboratory Fellow in the Theory Division in 1996, the highest scientific distinction at a United States national laboratory. He received the Alexander von Humboldt Research Award in 2005, was elected Fellow of the American Physical Society in 2009, received the Commander's Cross of the Order of Polonia Restituta from the President of Poland in 2012, and received the Los Alamos Medal, the laboratory's highest honor, in 2014. He was elected to the National Academy of Sciences in May 2024. LANL director Tom Mason noted that Wojciech's career at Los Alamos is notable for the many collaborations he has built, where he has set the very highest academic standards. And in 2025, he published what might be his capstone work, a book titled Decoherence and Quantum Darwinism, From Quantum Foundations to Classical Reality, with Cambridge University Press. I want you to hold the full arc of Zurek's life in your mind for a moment, because it tells you something about how science actually works, as opposed to how we pretend it works. A teenager in communist Poland reads Feynman's lectures and decides to understand the universe. He leaves his country, he finds Wheeler, he proves you cannot clone a quantum state. He explains how the environment selects what gets to be real. He spends 40 years at a nuclear weapons laboratory, not building weapons, but building a theory of reality. He's elected to the National Academy of Sciences at the age of 72. And the theory he spent his career developing, the theory that connects his work to Zeh's work, to Wheeler's work, to Everett's work, that theory says something about the nature of reality, that the establishment has spent decades trying to soften, trying to domesticate, trying to strip of its most disturbing implications. And Zurek, more diplomatic than Zeh but no less persistent, has spent those same decades quietly, relentlessly, pushing the implications forward. His 2025 book does not flinch. It follows the math, where the math leads. And where the math leads is exactly where Zeh said it leads in 1970. A Polish teenager buying Feynman's lectures under communism. A postdoc listening to Wheeler write wrong in capital letters on the blackboard. a theorist at the laboratory that built the atomic bomb, trying to explain why reality exists. That is the arc of a life that went from nowhere to the edge of the deepest question in physics. And now, I need to take you to that edge. I have been careful throughout this video to say that decoherence explains why you do not see superpositions, but does not explain why you see one outcome. I have laid out the proper versus improper mixture distinction. I have quoted the founders of the field. I have shown you the experimental confirmations. Now, I want to follow the implication to its conclusion, because that conclusion is the thing that Zeh spent his entire life insisting on, and the thing the physics establishment has spent 50 years trying to avoid. After decoherence, the state of the universe, the total quantum state including the system, the environment, the measuring apparatus, and you, is a superposition, not an abstract philosophical superposition, a concrete mathematical superposition specified by the Schrödinger equation. One branch of that superposition contains a version of the dust grain at location A, a version of the environment that has recorded location A, a version of the measuring device that displays A, and a version of you that sees A. Another branch contains a version of the dust grain at location B, a version of the environment that has recorded location B, a version of the device that displays B, and a version of you that sees B. Decoherence does not eliminate any of these branches. It makes them orthogonal. It prevents them from interfering with each other. It ensures that no measurement performed within one branch can detect the existence of the other branches. It makes each branch, from the inside, look like the only reality. But nothing in the math says any branch is not there. This is the point. This is what Zeh discovered in 1970 and what the physics establishment spent 2 decades refusing to face. The Schrödinger equation, applied universally without any ad hoc collapse postulate, predicts that every quantum measurement generates a branching of the total state into multiple non-interfering components. Decoherence explains why those components do not interfere. It explains why each component looks classical from the inside. It explains why observers within each branch perceive definite outcomes and cannot detect the other branches. What it does not do is explain which branch you are in. And now let me tell you the interpretations and what they agree on, because this is the part where retreat becomes impossible. The Copenhagen interpretation says, collapse happens. The wave function reduces to one outcome, but it has never specified a physical mechanism for collapse. When does it happen? Where? What triggers it? Decoherence provides no collapse mechanism. It just makes the lack of collapse undetectable. The many worlds interpretation says all branches are real. No collapse occurs. You are in one branch because you are in one branch. The other versions of you in other branches are equally real, equally conscious, equally convinced that their branch is the only one. Decoherence does not create the branches. The Schrödinger equation does, but decoherence explains why the branches cannot communicate. Ohmian mechanics says particles have definite positions guided by a pilot wave. Decoherence explains why the empty branches of the pilot wave, the ones not containing the actual particles, become dynamically irrelevant. The effective collapse happens because the pilot wave in those branches becomes decoupled from the particles. Objective collapse theories, GRW and related models, say the wave function physically collapses at random, with a rate proportional to the number of particles involved. Decoherence is supplementary in these theories. The real work is done by the collapse mechanism. which is a new physical process not contained in standard quantum mechanics. Cubism says quantum states are not descriptions of reality, but descriptions of an agent's beliefs. Decoherence is then a description of how beliefs update, and the proper versus improper mixture distinction is less relevant because the state was never a description of objective reality in the first place. These interpretations disagree about almost everything. They disagree about whether the wave function is real. They disagree about whether particles have positions. They disagree about whether the universe splits. They disagree about what collapse happens. They disagree about what quantum mechanics is even about. But they all agree on one thing. They all agree that decoherence is a real physical process. They all agree that it explains the emergence of effective classicality. They all agree that it does not, by itself, explain why you experience one definite outcome. The one thing every interpretation agrees on is that the hard problem of measurement remains unsolved, and the most straightforward reading of the math, the one that requires the fewest additional assumptions, the one that takes the Schrödinger equation at face value and does not add any collapse mechanism or hidden variables or subjective belief structures, is the Everett interpretation. All branches are real. You experience one because you are in one. The others exist. You cannot see them. Decoherence ensures you never will. Zeh believed this until the day he died. Zurek is more ambiguous, proposing what he calls the existential interpretation, but his entire framework of Einselection and Quantum Darwinism and extantons makes the most natural sense within an Everettian picture. David Wallace at the University of Pittsburgh has argued that decoherence plus the Everett interpretation constitutes a complete solution to the measurement problem. Many physicists disagree. The debate continues. It has continued since 1957 and shows no sign of resolving. But here is the thing I keep coming back to. Every experiment confirms decoherence. Every experiment confirms quantum Darwinism. Every experiment shows that the environment selects, records, copies, and distributes classical information exactly as the theory predicts. And no experiment has ever detected a collapse. No experiment has ever shown the wave function doing anything other than evolving unitarily according to the Schrödinger equation. The additional mechanism that would select one branch, that would make your experience of one reality the result of a physical process rather than a mathematical coincidence, has never been observed. We have been looking for it in various forms for nearly a century. We have not found it. And there is a reason for that. A reason that makes me personally uncomfortable in a way I want to be honest about. The reason we have not found a collapse mechanism might be that there is no collapse mechanism. It might be that the Schrödinger equation, applied universally, is complete. That every quantum measurement really does generate every outcome in separate branches of the universal wave function, separated by decoherence into sectors that will never interact again for the rest of time. It might be that the reason the math does not select one outcome is that no outcome is selected. They all happen, all of them, every time. I still do not know how to think about that. I have spent an unreasonable number of hours reading about this, reading Zeh's original papers and Zurek's reviews and Schlosshauer's textbook, and the experimental results and the philosophical arguments, and I still do not know how to absorb what it means if the Everett interpretation is correct, because it means that right now, as you listen to this, there are other versions of you doing other things, not in some abstract philosophical sense, in the concrete mathematical sense that the universal wave function contains components in which those versions exist, and those components are just as real as the one you are experiencing. And the only reason you do not know about them is that decoherence has made the branches orthogonal. You are separated from them not by distance, not by time, but by a decoherence barrier that was established in the first fraction of a second after each measurement event. And if you find that idea disturbing, you are in the company of nearly everyone who has ever thought about it carefully, including the man who spent his career working out the mathematics of how it works. Zurek, at the Santa Fe Institute, once said something that I think captures the emotional reality of working at the edge of this problem. He said the issue is not whether quantum mechanics is strange. The issue is that we have not yet learned to live with the strangeness. That framing matters. Not whether the universe is strange, whether we can learn to live with it. The environment has been doing this since the first fraction of a second after the Big Bang. Before there were atoms, decoherence was operating. Before there were stars, decoherence was selecting pointer states. Before there was anything that could be called an observer, the universe was already enforcing classicality on itself, already making copies, already distributing information, already splitting into branches that would never interact again. 13.8 billion years of continuous, unbroken, uninterrupted decoherence. Every photon that has ever scattered off every surface, every air molecule that has ever collided with every object, every gravitational interaction between every mass, each one a decoherence event, each one contributing to the manufacture of the classical world you inhabit, the process that makes your world look solid and definite and singular has been running for the entire history of the universe, and it will continue running until the last photon scatters off the last particle in the heat death of the cosmos. Even then, even in the final dying embers of the universe, decoherence will still be operating. As long as any two systems interact, decoherence happens. It is not a feature of complex environments. It is a feature of interaction itself. The universe decoheres because the universe interacts with itself, and it has been doing that since the beginning. There is a calculation that I find haunting. In the very early universe, roughly 10 to the negative 36 seconds after the Big Bang, during the epoch of cosmic inflation, quantum fluctuations in the inflaton field were amplified by the exponential expansion of space into the density perturbations that would eventually become galaxies. Those quantum fluctuations decohered. The environment of the expanding universe selected certain configurations, certain density profiles, certain patterns. And those patterns, frozen into classical definiteness by decoherence before the universe was a trillionth of a second old, are the patterns you see in the cosmic microwave background today. The patterns that became the filaments and voids of the large-scale structure of the cosmos. The patterns that determined where galaxies formed, where stars ignited, where planets coalesced, where you were born. The classical structure of the observable universe, the entire web of galaxies stretching billions of light years in every direction, was selected by decoherence in the first fraction of a second after the Big Bang. You have never once experienced the quantum universe you live in. Not once, not for 10 to the negative 31 seconds. The environment has been too fast, too thorough, too complete. Every object you have ever seen, every surface you have ever touched, every person you have ever spoken to has been presented to you only in the version the environment permits. the environment selects what gets to be real for you. The environment copies that selection and distributes it. The environment makes sure everyone agrees. And you call the result reality. You call it the world. You call it objective. And you have never questioned it because the mechanism that creates the illusion of objectivity operates faster than light crosses a proton. The question of physics discovered in 1970, buried for 2 decades, confirmed experimentally in 2019 and again in 2025, and still cannot answer, is whether the versions the environment does not let you see still exist. Zeh thought they did. He thought they were all equally real. He thought you are one branch of a universal wave function that has been branching since the origin of time, and that every version of every outcome that has ever occurred or ever will occur is still out there, separated from you by a decoherence barrier so complete that no signal, no measurement, no experiment will ever breach it. He thought the fact that you can never know about the other branches does not make them less real. It makes them more real, because the only thing preventing you from seeing them is the same process that makes your branch look like reality. Decoherence does not create classical reality out of quantum mechanics. It creates the appearance of classical reality. And the appearance is so perfect, so seamless, so complete that you have never once in your entire life questioned it. Until now, Zeh is buried somewhere in Germany. His paper is still in volume 1 of Foundations of Physics. The numbers he and Joos calculated have been confirmed to arbitrary precision. The environment is still watching, still copying, still selecting, still manufacturing the world you experience at a rate of billions of events per second, for every object within your line of sight. And somewhere in the mathematics, in the full quantum state of the universe that the Schrödinger equation describes, there may be a version of you that stopped watching this video 5 minutes ago, a version that never started, a version in which Zeh's paper was celebrated in 1970 and the field advanced 25 years faster. A version in which Wheeler's brother came home from the war, and Wheeler never asked whether the past could have been different. A version of every choice, every measurement, every scattering event that has ever occurred. The math does not say they are not there. Nothing in the physics says they are not there. And the last thing Zeh wrote, 3 weeks before he died in the Black Forest, was that decoherence had been experimentally confirmed. He did not write that the measurement problem had been solved, because he knew. He always knew decoherence was never the answer. It was the thing that made the question impossible to ignore.